Hello, so today we are doing this problem called merge intervals. And so the problem says we get a collection of intervals and we want to merge all overlapping intervals. And so for example, we get this list of intervals, and so this here is the first element is the start of the interval, the second element is the end of the interval, and we want to merge them. So for example, here we have the interval 1 3 and 2 6, and so to merge them, because 3 here is less than the end of this interval, we have from 1 to 6, and basically you get the idea. That's how what we want is basically to go through them and merge them. For example, 1 4 4 5, they overlap because 4 here is equal to the start here, and so we get 1 to 5. And so this is what we wanna do. Now let's look at how we can solve this problem. Okay, so let's see how can we solve this problem. So let's first look at the first example, right? So the first example looks like we have this list of intervals 1 3 2 6 8 9 8 10, sorry, and then 15 18, right? And so you can see in this first example here we have this interval 1 2 3, and then we have 2 3 4 5 6, and then we have 8, so 8 is like 7 here, and then we have 8 9 10, and then we have 15 up until 18 somewhere down here. And so you can see these two here in this section are overlapping, right? And then these two stay the same. So what we end up having is this. So that's the result that we need to return, is something like this. And then this one stays because they are already disjoint, and then this one stays the same. So you can see this final result, nothing is overlapping. And so basically what we need to return for this case is 1 to 6, and then 8, 10, and then 15, 18, sorry, 15. Okay, so let's see what can we get that will help us. So the key point seems to be here overlapping, right? Intervals that are overlapping or not, right? And so let's see here what we should do. So what we are looking for is kind of defining a formal definition of overlapping intervals. So let's say if we have two intervals, let's call them I1 and I2. So what should happen here? So we have so for them to be overlapping, we have to have, for example, this case I1 and then I2 here, right? And so this is its start and this is the end of it, and this is the start of this one, and this is the end, right? And so the requirements that we have in this case are the following. So we need I1 start, so I1 end actually, so I1 end okay, let's take another different case here. Let's take the case where they are all overlapping like this, so something like this maybe, right? And so this is the end of it. And so in this case we don't care where the start is, like, right? Because the start may have been here, right? This case is still handled. And so what would happen is I1 end would be bigger or equal, so it maybe also it's here, so we are handling all these cases, is bigger than I2 that start, right? So I1 that end is bigger than I2 that start. which is here, which is this one. This one is, sorry, which is this one. And this is I2.start. So you can see this one ends after E2.start. And so you can see in the picture they are clearly overlapping. The other requirements can be that I1, the start of I1 is less than or equal to the end of I2. So the start of I1 less than or equal the end of I2. So you need this, you need basically the start here, either here or here, you need it to be less than the end, otherwise they are not overlapping, because otherwise if this is not valid, you can end up with a case like, let's say you have something like this, and so for I1 start to be bigger than maybe something like this. So in this case, we do have that the end of I1 is bigger than the start of I2, right? But they are not overlapping because the end of I2 is smaller than the start of I1. So you need this condition for them to be overlapping. And for the first condition, if you didn't have it, so you might have, let's say, if you didn't have the first condition, then what we will have is I1 dot then we will have I1 dot end is maybe less than I2 dot start. And so to visualize that one is, let's say we have, this one is smaller, so we would have I1 here, and then we'd have I2 here. Start, end, start, end. And so you can see here they are not overlapping. But we have that I1 start is actually less than I2 end, right? But this one is not, the first one is not valid, and so we do need these two requirements for our intervals to be overlapping. So this is requirements for intervals to be overlapping. And so from this analysis, so right now what we did is just we took overlapping intervals and we formalized it into something that we can work with. And now, so let's see this. So using this, what we can derive is if we sort the intervals by starting time, then what will happen is that we will have, let's say I1 was before I2. This would be valid also if we have a different case, sorry. So if we have I1, we don't care when did it start, but let's say just I2 starts after I1. So is less or equal to I2.start. So we know that I2.start is less than or equal to I2.end by definition of the interval. And so already we know that I1, because we will be traversing them in order, so we will be saying for I1 so we'll be saying for I in the intervals, and so we'll be going from the first interval so in sorted order to the second interval in sorted order. So we would have this verified, this condition would be valid. And so this condition says that I1.start is less than or equal to I2.end, which is the condition 2 that we had over there. And so by this, that means that by simply sorting, so by sorting using start time, we can guarantee that condition 2 or requirement 2, And now we only have to do is find 1, and then we will know that we are overlapping, right? And then adjust, which means basically what I said here, which is, or what we've done here, which is go from this thing that was overlapping to this interval here, right? Okay, so now that we have this, let's see how can we apply it to get our solution. So the way we can apply this is just we can sort the first step of the algorithm would be to sort intervals by start time to get the property or requirement number 2. And then the second step would be to go through the intervals, right? So go through the intervals, sorted of course. And when 1 happen, which occurs basically, let's call it, then adjust the interval. What does adjust the interval in this case mean? And so what is, first let's just see what is 1 here. So 1 says that so 1 here says that we would need to have this here, I.1, so sorry, 1 is this. So if we encounter an interval such that the one we already stored in the output has the end bigger or equal than the start, then what we do is we adjust the interval so that its start becomes the minimum of the 2 starts and its end becomes the maximum of the 2 ends, right? Because what we want to happen is, if we have the 2 intervals that have 2, basically what we want them to have is, we want to do something like this. If it's like this, then what we want to end up with is something like this, right? And then if we have something like this, let's say this one is the smaller one, this one is the bigger one, then what we want is to end up with one that's, so you can see the start, we want the start to be the smaller of the 2, this one in this case, and for the end what we want is, we want the bigger of the 2, which is this one here. So you can see the bigger of the 2, right? And so this is what we are going to do when we find the condition 1. So if 1, what we are going to do is we are going to have the interval be interval to add to the output is going to be the min of, let's call one of them is I1 start and I2 start. That's going to be the start, which is the first element, and then our end is going to be the max of I2 dot start and I2 dot end. I1 dot end and I2 dot end. But there is something here, because we already ordered them by start, right? And since we are traversing them in the right order, we know that we don't need to change the start. And so what we need to do is just take the last interval, let's call it last, or the previous interval, right? So let's just call it the previous interval. And then let's change its end to be whichever one is maximum, because we know this one we already have the smallest start in is the previous interval, because we are processing them in order. And so what we are going to do is just say the previous end is going to be equal to the max of the previous end and the current one end, right? And that's pretty much it. And so let's just write a short pseudocode for this here. So So what we are going to do is first we are going to just sort intervals. So that would mean we are going to have something like this. So we are going to take our intervals and sort by start time, which is just the first element, right? And then once we sort the intervals by start time, now we can just have our result, which would be what we have in the example that we did earlier. It would be this here, the after merging the overlapping intervals. And so that result, what we are going to do is we are going to go through the intervals, and we are going to call them current. And we are going to say, we are going to go through the intervals. So either we haven't put anything in the result, and in that case we don't have a previous one yet because we haven't processed any one yet, and so in that case we are going to just add it. And so I'm going to do it here, result add the interval, right? And this is going to be else of something else. And so here this else is when we don't have any intervals, no intervals added yet, or something else. But if here we do have the result is already filled, so we already have a previous interval that was already added. So if result in Python, this just would mean just that there is already something in it. I know this is pseudocode, but this is just easier to write. And so if either that or we had so that means that we have a previous element. So now we are going to look at condition 1, which is the previous end is bigger or equal to the current start, right? And so the previous is just the last element in result. And so here we can just say previous is equal to let me just write it here to be easier. So previous is just going to be the last element, and so we can just say result something like this to get the last element. We can do this in Python, and we can do the property 1 that we just defined here. If this is bigger or equal to the start, the current interval start, which means this is basically the property 1 I was talking about, then at that point we can just do the adjusting that I mentioned here. So we can just do that here. Otherwise, that means either this one doesn't contain anything, or it means that this condition is not verified, so it's less. So that means we don't have any overlapping intervals. And so if it's not overlapping with anything, we can just add it. And at the end, we will have our result here. And so that's pretty much it. Now let's just code this up quickly and submit it and see if it passes. Okay, so now let's do the let's do the solution here, and on Leetcode, the same solution that we just described on the concept concept of the solution, and then let's see if it passes. And so what we did was first we sorted the intervals by start time, and so that would be something like this. And we need to sort them by start time. So in Python, that would be just using lambda x and then saying we want to sort them by start time like this. And then we're going to have this result here that will contain our result. And then we are going to go through the intervals in the same way that we did there. And then we are going to check the same way if we have results, something in there already, and if the first condition that we mentioned was valid, which is that the last one that we just added, which is the previous interval end, which is at position 1, is if that is bigger or equal to the start of this current interval that we are processing, and so that would mean current 0, then at that case we can extend the interval end, right? Because we are guaranteed that the previous interval start is smaller, and so what we can do is just say result.end is equal to the max of result minus 1. That's the previous interval. Max of result minus 1, which is the previous interval, max of its end value, which is 1, and the end value of the current interval, which is current 1. Otherwise, we are going to just add it, because either the result doesn't contain anything, so we don't have a previous interval at all, or the result, the previous interval end time is less than the current interval start time, and so they are not overlapping, and so at that point we can just append the current interval, and after that we can just return result. Okay, so let's run this, and then so there is one syntax error. It should be lambda x like this. And we shouldn't. We don't need this space. So we did. So either we have something in result. Yep. So it's not end. It's end is the last element of the list composed of only 2 elements. Because that's just the structure of the input. It's the start is the first element, the end is the second element. So you can see here we do have a good set of intervals here, so it works. Let's just try with something like an empty one like this. Just some edge cases to make sure we didn't mess up. 3, 4, like this, and then maybe something like a huge 110, and then maybe let's just take the rest of these, so that okay. It's taking a little bit of time. Okay, so we have an expected character. Maybe the input can't accept. Let's just submit and see. See the verdict. Okay, so it passes, the solution passes. Okay, so next we will look at another way to solve this problem. Okay, so the other way to solve this problem is using connected components. So let's just look at the example that we had before again one more time. So that example was a list of intervals 1 to 3, 2 to 6, 8 to 10, and 15 to 18. And so essentially, so the other way to solve the problem is connected components. But how can we solve that? So the thing is to try to represent this as a graph, such that 2 nodes are connected if they overlap, right? So that would mean, for example, here we would have 1, 3. Since it overlaps with 2, 6, we are going to draw an edge between them. So the nodes are the intervals, and the edges are between 2 nodes if they overlap. And 8, 10 doesn't overlap with any other interval, so it's a node by itself. Same thing for 15, 18. And so with this, you can notice we have this interval here, this components here, and then we have this component, and then we have this component. And so a component can have something that represents the component. So that something can be called the parent or the root. There are different terms that you can use it for. And so here our parent or root, we can make it be the overall interval merged. So basically we can take the min of both starts and the max of both ends. So that would be 1, 6 here, and this one is just the same since we didn't change anything, since it's just one node.
and this one, since it's just one node, it would be this. And so we will end up with these intervals. And so at the end, we will have something like a set of intervals which is the answer, 1 to 6, 8 to 10, and 15 to 18. Okay, so this is the idea. And basically what we have here is this is one of the connected components, this is one of connected components, and this is the other one. And so connected components, finding them, you can use multiple methods. One of them is union find, and another one you can use DFS. And so I'm going to use DFS because it's easier, but one note about this solution is that theoretically it should work, but when I did test it with Leetcode, it always gives a time limit exception or exceeded on the last couple of use cases. But I think it's a good solution to have, or to have, like, so that in some problems the only way to solve them is this. And so knowing about this way to solve the problem, basically having something that initially doesn't look like a graph, but then converting it to a graph, and from there applying one of these methods to find the connected components, and then from those extracting whatever information you need, which in our case here, it's the overlap, the interval after merging them, right? Okay, so let's jump into code and code this up using DFS. Okay, so now let's do the DFS implementation of this, basically of finding the connected components so that we can find and merge the intervals. Okay, so first thing we need to do is have something that builds a graph that we did in the explanation earlier. And we said that we need to know whether two nodes overlap so that we can have an edge between them. So we need a function that can determine the overlap between two intervals, A and B, let's call them. Another thing that I want to use here is a class interval, because I get lost if it's like 0 and 1s and make mistakes using that. And so let me just define a class, right? And then just label them so that the coding becomes easier. So we need a init function, and we are going to have a start and an end as input. And so let's set our start function and our end function. And so now when we need to build up a graph, and we need to have a way to construct the connected components so that we can know the representative or the parent of each connected components, and then we can from there get the merged intervals, right? So we need something to build the components using, of course, the graph that we would have built earlier, and that's pretty much it. And so this should return at the end some graph, this at the end should return to us a set of components that are just the list of intervals after they have been merged. And so with this, we can just, the skeleton of this, we can return the final result. But since I wanted to convert the list, since the input is like this, I want to convert it to something where I have an interval class so that I can have it easier to access. So I'm just going to do that here. So for each interval, let's call it I in intervals, I'm going to create just an instance of the interval class that I just defined, and the start is just I0 and the end is just I1. So this will just make the rest of the code easier for me to write. Now we need to build the graph, so we are going to build the graph like this, and then after that we are going to build the components using that graph and return that, because that's the list of the intervals after being merged. That's what I expect my method to return. And so first let's build the graph. And so
let's just initialize it to a map, right? That's a map from a node to its adjacent nodes. And we need to go through the intervals, right? So I'm going to go through the intervals, and for each interval I'm going to go through all the other intervals so that I can check if they overlap with that interval or not, so that I create an edge if there is if they overlap. And also I forgot to mention that this should be an undirected graph, because if two nodes overlap there is no real direction, right? And so what we are going to do is we are going to do b in intervals of all the intervals after I, so I plus 1, like this. And one thing here, I'm just going to initialize a list for this node so that I can add to it its neighbors. But I should initialize it only if it doesn't exist yet in the graph, so if it hasn't been processed before, right? So if not in graph, then I initialize it. For b, I do the same thing because this is an undirected graph, so I'll be putting in both of them. And so b not in graph, then initialize it to a list. I could have also used collections.default dict list to avoid doing this, but yeah, both are the same. So now I check if they are overlapping. I create an edge between them, so that would mean graph of A, append B, graph of B, append A, since it's an undirected graph. And I need to define overlapping, right? So when do two intervals overlap? So either the start of A is less than the end of B, right? The start, so let's say we have something like this, where this is A, so this is the interval A, and its start is less than its B dot end. So that would mean it started here, and then B is like here. So they overlap because the start of A is less than, sorry, the start of A is actually like this. So the start of A is less than the end of B, right? It can be like, it can be even like, because it can be even because B is too big, like this. But what's important is that the start of A is not after the ending of B, and the start of B is so the start of B is less than the end of A, right? Because if it's not, then we might have a scenario like this. The start of A is still less than the end of B, but they don't overlap. So we need the other condition for the start of B to be less than the end of A so that they can overlap, right? Okay, so that's the overlap function. Now all we need to do is do the components, but for that we are going to use DFS. So I need a function that does DFS that will have some parameters. So the way to do the connected, so let's first define the components that we are going. So one thing I forgot to mention, this is just the representations of the components, which is the merged interval as I explained in the explanation earlier. And we need a visited set so that we don't go over the same node multiple times. And so with the components initialized to an empty list, the visited set, and with the index start out as 0. So now we are going to go through the nodes in the graph, and we check if the node hasn't been visited yet. Then this is just the standard way of doing connected components. And so we are going to add first the current interval, which is node.start,
node.end, right? And then when we go and find something that is connected to that node, we are going to check if it's if the end and the starts of the new nodes are better, then we are going to replace them. Otherwise, so we are basically going to replace with a merged interval. So we are going to take the better start and the better end and make that the new parent. And the new parent is just what's in the components, right? So now we are going to traverse the graph using DFS to find all the connected nodes to this node. And the connected node, remember, is just the node that overlap with it. So those should be merged with this interval so that whatever is here becomes, whatever is at components index becomes the merged interval, right? So we need to pass the node, we need to pass the visited set, and we need to pass this here that contains the merged interval, right? So which is components at index. Why components at index? Because it's at 0 and then we append an element, and then at the end I'm going to increment it for the next iteration to append, and for whatever it appended would be at the components index, right? And so now we need to define this here, so it gets past a graph, a vertex or a node, and then an array of the connected components here, or let's call it just interval because it's the merged interval, and then a visited set. And so what's going to happen is we need to first add the visited node, right? And then we update because here we are going to go through the neighbors of that vertex, right? And check if that is not in the visited set, then do DFS on it, so graph, so that we can find the connected nodes to that one, because that's what finding a component entails, and then the neighbor here, interval and visited. But the operation that we need to do here is merge the interval. So here we find something connected to it, which means overlapping, so we need to merge it with it. And merging means that the interval start, which is 0, is going to become the minimum of the interval start that we put here, or that we will put in another pass, and the start of this interval that we are looking at, which is the node start, right? Remember, what we put in the graph are the nodes in this format, right? And then the end is going to be the same thing, the end of the current, but the max, however, because that's where it ends. So the max of the current of the interval that we put before as the representative of the components, and the end of this vertex, because whichever one is bigger, the merged interval will take that one as the end, right? And that's pretty much it. So this is the DFS implementation, and once we go through it for all nodes in the graph, we would have all the connected components, with components containing the representative of each component. And that's pretty much what we need to return. Where was this? Line 23. Yeah, so if B is not in the graph, initialize it. What? So this is I+1. Yeah, maybe it's because one of these, I'll just leave the... Okay, so it looks good. I'll submit. Okay, as I said earlier in the explanation, it gets time limited exception on the last use test case 169 because it's a little bit slower, but it's a good to know explanation, good to know solution.
And the overall time complexity is of this is we are doing DFS, but we are doing it for each node. It may degenerate to be for each node, and so it would be O of V plus E multiplied by the V, so the number of nodes. And so basically that's O of V multiplied by E plus V, and this one is the number of nodes, so the number of intervals, let's call it n, and the edges at most we will have, let's say if each one was mutually overlapping with the other one, we'll still have n, and so that would be plus n, and so overall it's O(n) squared plus O(n) 2n squared, and so it's just O(n) squared overall. So the previous implementation was better because it was an O(n) solution, right? But this one is nice to know. Yeah, so that's it for now. Thanks for watching. See you next time. Bye.